Yeah, please.
Okay, so I'm saying that the signature is a set of constant function and relational symbols. And what I want to say is that when I will be talking about models, because we will be talking about models quite a lot here, what I mean by a model over this signature sigma, so a sigma model is such a tuple, so I'll use this mathcal font, which consists of a domain. So I will use the same letter, but normal, let's say, which is a finite or infinite set of domain elements. And that it consists of interpretation of constants for all constants in my signature, as well as functions in all in my whole signature, as well as these predicates or relational symbols. So the interpretation of all of those in my signature.
But about the terminology, sometimes people speak about model of a theory, and you use the same word model for the case when there is no theory, there is just any structure.
Yes, so for me, model, let's say, is just a structure. So I'm talking about structures. I'm not saying what does this structure satisfy, what kind of theory it has. I'm just saying that this is a first-order logic structure. Let's say that I will use structure and model in the same meaning.
Yeah, but also you will say about model of a theory, I guess, at some point.
That's true. That I will be talking
maybe it's maybe if you don't mind, you can use more the word structure when you to avoid.
That's perfectly fine. So I can talk about how can I erase it?
No. We will accept this too, but just if you say structure, it will be more less confusion.
Okay, that's fine. So yeah, this M is a finite or infinite set. So we'll be considering finite and infinite models. Each of those interpretations of a constant is an element of M. Each function is interpreted as a function from a tuple of elements in M into an element in M, and every relational symbol is interpreted as a subset of M to the power of N, where N is the arity of the predicates. Okay, so is it clear, or do we need any example of a structure?
No, I think we should assume that this is known, because if it isn't, probably there is no chance. So I think we can move.
Okay, so I will be talking about this, and then I will be talking about preservation theorems. So preservation theorems have the following form. They have the form of an equivalence. And this equivalence says that an FO formula is preserved under something, which I will explain in a second. If and only if this is the case that this formula, let's give it a name maybe. So I want to say that this, let's give this formula a name phi. So if and only if phi can be expressed, so it's equivalent to a formula in some fragment of first-order logic. And then depending what you put in the space of these three dots, then you obtain different preservation theorems. So formula, actually, if you would like to be more precise, we are talking about
closed formula. guess. And equivalent means that it's provably equivalent. There is a formula in this fragment where the equivalence is always true or provable.
Yes, so by equivalence, I mean that they have the same models. So every model of this formula is also a model of it's the second formula in this fragment of first-order logic. They have exactly the same models. So now probably what requires explanation is what does it mean preserved under and what kind of functions we will use here, as well as what kind of fragments of first-order logic. So maybe before even stating this, notice why it's interesting to have such a... Oh, maybe let me at first explain what will be on both sides. So first of all, if we have some operation R here, so what does it mean that a sentence is preserved under... Can I copy? Let me see.
No, there are three famous classes. Universal formulas are preserved under going to a smaller model. Existential formulas are preserved when going to bigger model, and for formulas of forever that exist are preserved when we go to a chain of models.
Yes, exactly. So can I copy this, duplicate? Do you know if...
No, but I guess just if you can just write this on the board, not moving things, because on the screen it's not easy to follow. It will be, for us, it will be better.
Okay. So you said already the three theorems which are here. So maybe I can write it. So one of those, probably the first one, is by Losz-Tarski. So this is theorem which is called Losz-Tarski. And this is because it was proved by these two gentlemen independently. I think Losz paper is from 1954 and Tarski paper from 1955 around. And this theorem says that the first order sentence is preserved under, we can think about being submodels or extensions. Let's say that we are talking about induced submodels or substructures.
Which means we have a subset which is closed under functions, and then we consider a natural model there.
Yes, so preserved under induced substructures, I don't know if I should write it down, but maybe I can say it in words. So it means that whenever I have a structure which satisfies this formula phi, so phi holds in the structure, and I'm looking at the induced substructure of the structure, then phi also needs to hold there. Well, this induced substructure, where this is a substructure, so it has the domain which is a subset of the big model, let's say. But everything which holds over these elements of this smaller domain in the bigger model holds also in the smaller model. So this is an isomorphism between this smaller structure and its image. Is it clear? Or
functions? We have functions. It's not always.
Yeah, the smaller domain should be closed under all functions. Otherwise, it's not allowed.
Okay, yeah. Mm-hmm.
Yeah, and fragment here is the universal formulas.
Yes, is
okay. Maybe you should not move the screen, because we try to follow you, and that's difficult because when it goes out of the screen. Yeah, it's in the universal fragment.
I think everybody should be able to move on their own the whiteboards, no?
No, it's true. That's exactly the problem. We have it on the screen, and then you move it, and then we don't see what we see before, and need to do something. So if you just do it rarely, it will be much more convenient.
Okay,
but,
all right.
Okay, we can follow, of course, but if just it's not. universal formula.
And the universal,
And by universal,
yeah, sorry, that means that there are some quantifiers, universal
And then a
quantifiers.
formula without quantifiers.
So, but
so this is the
can I ask
universal
a very,
formula.
very uneducated question? So, there is a standard thing. If I have a first order formula, I can get rid of existential quantifiers.
What do you mean? Get rid of?
I
Just
can.
replaced by negations.
Yeah. So, but then negation are left outside. So that's why. I
No,
mean,
no,
I
no.
can.
No, just the context is like this. Every formula can be translated to a form when we have first the quantifiers and
Yeah.
then the but we cannot if they have many quantifiers forever exist, we cannot do anything. And the simplest case is when there's only one type of quantifier, and this is universal formula.
No, yeah.
Univer-
And I
and
just made a simple remark why. I mean, there is a standard fact that you can express universal quantifiers with existential, but then when you express a existential with universal, but when you express existential, then you also leave some negation outside.
Yeah, so it's exactly, you can write that not phi is equivalent to formula there exists one, there exists x1, there exists xn, not psi.
Yeah.
Yeah, so we're looking at this Prenex normal form formally. So I think this is the equivalence that you were mentioning, but of course you can do this. But if you are looking at this Prenex normal form in which you've got only a block of universal quantifiers and then psi, which is a quantifier-free formula, then you cannot do this. So this is universal formula.
And if we switch to not phi, we can reformulate this theorem in terms of existential formula. If not phi is preserved under induced substructures, which means that phi is preserved under extended substructure.
Is that clear?
Exactly.
Wait. What is?
Please don't do this.
Because I have not enough space on my
Sasha.
my
Honestly, like the Przemysław was suggesting to use other thing. You said we want to use Zoom whiteboard, and then you're complaining that Przemysław is using Zoom whiteboard to be.
No. Just not complaining about anything. I'm just pleading.
Sasha, we should keep in mind that there is also a problem on the speaker's side, because he needs somehow to write new lines. We don't know how large is this scope on his tablet. Perhaps it's unavoidable that he moves.
No. From time to time, it's okay. But just I'm pleading. No, if it's not possible, no problem. But if you can minimize this, it will be convenient.
Because I wanted just to move, because what you said now is important observation. So if we replace here now, I would like to draw in red, instead of having induced substructures, if we talk about embeddings or extensions, which is the other direction. So it's the reverse direction of being induced substructure. Then here, in the place of universal formula, we will have existential formulae. So these two statements, these two preservation theorems are equivalent, and it's quite clear that it is the case. Okay?
Why is it either? Are they equivalent? Is it?
No, because if phi is preserved under going down, then not phi is preserved under going up. It's just both things mean that we cannot have phi in the smaller one and not phi in the bigger one. So phi in the bigger one and not phi in the smaller one.
Yeah, probably. Yeah.
And
But we
if
can-
phi is equivalent to universal formula, then not phi is equivalent to its negation, which is an existential formula.
But we can focus on this first one, so we can forget about the other one and focus on the first one. And this is, let's say, what I can call Losz-Tarski theorem. But yes, it's phrased in different forms because it's really equivalent. So this is Losz-Tarski. And then we've got other as well. So if let me try to do this. So another theorem is called Lyndon positivity theorem. So it was proved by Lyndon in 1959 now. And it says something similar, but it says that if we have now being preserved under different relation, and in this case, it will be surjective homomorphisms. Then this formula needs to be positive formula. And positive formula, I mean a formula which allows for universal and existential quantifiers, but it does not allow using negation at all. Okay? And one more famous is homomorphism preservation theorem, HPT, how it is sometimes abbreviated. Homomorphism preservation theorem, what it says is that if we now have homomorphisms, then a formula that we need is a formula which is existential positive. And by existential positive formula, I mean a formula which is existential formula with no negation.
And positive formula, it just has no negations, and but it can have quantifiers in any order, in any quantity, and so on.
Yes, exactly. So I think those are the three main and the first preservation theorems that were introduced. So maybe an observation that I made. So I was looking for a history of this and why people started working on this. And what I found out is that people often refer to Professor Edward Marczewski. So he was a mathematician in Poland, in Wrocław. And he's said to ask the following question: which FO sentences are preserved under surjective homomorphisms? I think he was algebraist and he was interested in had some algebraic motivations to ask this question, but I don't know any paper in which it was stated. It's some kind of a folklore in this research area. And this is what people say started this line of research.
Excuse me, I don't understand actually Lyndon theorem. What do you mean by surjective homomorphism?
No, just we have a homomorphism.
What is homomorphism?
A surjective mapping of a set, underlying set, which preserves operations and predicates in a natural way.
Okay, assume that we have only one predicate of zero arity.
Zero arity, so it's just a Boolean variable.
Yeah, Boolean variable.
Yeah.
So what does it mean, surjective homomorphisms? That means that the interpretation of this variable is preserved, right?
Yeah. So you say why the formula not P is not...
No, not P is not a positive formula, but it is preserved under surjective homomorphism, right?
Yeah, indeed, something doesn't fit here.
Not P.
So exactly. So what is this sentence again that is preserved under surjective homomorphism?
No, we have only one predicate, which is of zero arity, which means that it's just a Boolean variable, either true or false. No. And it is not preserved under surjective homomorphism, I guess.
Why it is not?
So what's the definition? It should be that for every input to a predicate, if it's true in the initial formula, so in the initial structure, then it's true for the image, right?
Yeah. And if it's false, it should be false for the image, or not?
No, because it's just
So it can be false under the homomorphism and true after. Yeah. Homomorphism is not preserved. Predicates are preserved, but if they are true, they are still true for images, but not vice versa. This is what we understood incorrectly.
No. So say it again. What is surjective homomorphism? What does it
For
mean?
example,
No,
in the
surjective
graph,
means surjective. It's nothing. It's additional. But homomorphism is if something is true for the pre-images, it is true for images. But if something was false for pre-images, it can be still true for images.
so can you give then an example? So we have just a formula not P, where P is just like a propositional variable.
Yeah.
So under which subjective homomorphism it's not preserved?
It's false before the homomorphism and true after the predicate. So the form will not P is not preserved.
So if it's false,
it was true
if P
above.
is false, then there are no requirements about the.
In anything, no
So we can just
requirements
say that
about
to be
anything.
true. Okay. Yeah.
Yeah.
But formula P, just without negation, you cannot do that.
No, if it's positive formula, then you can prove by induction, using this surjective homomorphism, that it will be true for the image. Because for conjunction, disjunction, it's clear.
But I don't understand. What is then also preserved under? What does it mean?
If it was true for the pre-image structure, then it will be true for image structure.
So it's not that the value of the formula is the same.
No. Formula is for the structure. The formula is either true or false. It's a sentence. It's closed.
No, I mean then it's like value.
The value can become true while being false initially.
So is it correct that in all these theorems this is the same understanding? So if I have a formula that was true, then we are saying that it will also be true in induced substructure, under subjective homomorphism, and so on, in that sense.
Yes. If it's true in structure, in initial structure, it also true in the structure obtained by either induction, this induced substructure, or homomorphism, or whatever.
Okay.
Yeah.
Yes, and it's crucial that it's just one direction.
Yeah.
So if we have two directions, usually people talk about invariance.
Yeah.
But this is preservation. So something being true preserves, it still is true after application of some operation. Okay.
Yeah.
So maybe important observation before I start proving stuff, because the plan that I had was to prove the Losz-Tarski theorem. is to observe the following. The first two theorems, so these two, do not hold in finite. What I mean by this is that if we say that now preservation under induced substructures, for example, is a property over only finite models that we are interested in, then it's not the case that a first-order sentence which is preserved under induced substructures over finite models is equivalent to a universal formula.
And equivalence is
Similarly,
also only over finite models.
sorry?
Equivalence
When you
is
say equivalent, it means that it's equivalent in all models or only in finite models.
So the theorems that I showed on the left side are for all models, and now I'm claiming over finite models.
No, you say that for final models it's not true. But
Yes.
when you say that it's not true, how do you understand the word equivalent?
Over finite models.
Over finite models.
Yes.
And is there some simple example you can show us now, or it's something complicated?
I can show you, but it's not easy. So I can
Okay,
either start
okay.
by proving Losz-Tarski theorem,
As you wish. Yeah, if it's not immediate.
or I can show that it does not hold infinite. But I wanted to at first make this statement because actually it is, I think, interesting to observe that some properties like this hold over arbitrary but not over finite models. And another interesting observation that I only marked these two theorems, but not the third one. So the third one over finite models was for a long time question mark. It was an open problem, and it was proved only in 2005 by Rossmann. It was said to be the biggest open problem and biggest result in model theory of recent decades that this holds.
Wow.
So it holds over finite models.
And you know this proof, so you can, or not. So maybe it will be nice if you can teach us this. After,
Not today
of course.
for sure, because it's not easy proof.
No, but if you know this proof, it will be a nice thing you can learn from you. But
I
Yeah,
mean,
we
we're not saying that you have to give it now. Maybe some other.
yeah. No,
Seminar.
just no. And it doesn't mean that you need to learn it specially for us. But if you already know this, it would be fine addition if you once prove it.
No, I've seen the theorem, so now I would not be able to prove it. But if I think more, I should be able.
Yeah.
So the two things that I wanted to, okay, so this is for first order logics. So HPT being homomorphism preservation theorem is almost the only one which holds over finite models still. The situation is very different in modal logics, in which we've got many more results which hold over finite models. But this I will not touch as well today. So the question is, what order do you prefer? I can either start to prove Losz-Tarski theorem, or I can show that it does not hold over finite models, and whatever you prefer.
No, I guess since Losz-Tarski is easy, maybe we should start with this easy thing, and then go to a more difficult example.
Okay, I mean, yes. I think the hardness is quite similar of both. So there are probably many ways to prove, let me put it nicely. So there are many ways to prove Losz-Tarski theorem. I will go with one of those. I don't know if this is the easiest or no. Let's see. And I will be using two results for this. One is compactness theorem for first order logic, which is a well-known result by, well, it was proved that the completeness was proved by Gödel in 1929 in his PhD thesis, and compactness follows immediately from this. I don't think he stated compactness in his PhD thesis though. So let me just state what compactness is, because this may help us. So compactness theorem says what follows. So for every first order logic theory. And by theory, I mean a set of sentences of first order logic, which can be finite or infinite. This is the interesting case when it's infinite, of course. The following holds, namely, this theory is satisfiable if and only if T is finitely satisfiable and by satisfiability, I mean existence of a model, so a structure in which this theory holds, so every sentence of this theory holds in the structure. And by finite satisfiability, I mean that every finite subset of this theory has this property that it has a model. So one direction is, of course, clear. The other was the interesting one and follows from completeness. I will not maybe go into more details. I will assume that we know compactness. I will use it.
Yeah.
So this is the one result that I will use, and this is significant. And actually, this is one of the reasons why Losz-Tarski does not hold for finite models, because in finite, this theorem, compactness theorem, does not hold. So it essentially, Losz-Tarski proof essentially uses this theorem. And the second one is a technical lemma, which I would like to prove, because it's maybe not that clear. So it says what follows. Let me take a formula phi. So it's a sentence. So first order logic. And let T be a theory which has this property that it is closed under disjunctions. Which means that if I have two formulae, then the disjunction of these two formulae is also in this theory.
That's strange. The disjunction is weaker, so if we just close the theory under provability, it's automatically true.
Yes. So this
Okay.
holds for any theory which is closed under disjunctions. Yeah.
Okay.
But let me make the statement at first, maybe.
Yeah.
And I want to have this formula phi and theory T, which additionally satisfy the following property. Whenever I have some structure A, which satisfies formula phi, so if this holds, and moreover, I have another structure which satisfies a theory consisting of all first order logic sentences in my theory T above, which holds in A, then B also satisfies formula phi. Okay, it may look a little bit ad hoc at first.
No, so phi is not in T. Yeah. So this is which makes this interesting.
So I didn't finish the lemma statement, right? I'm just saying let's take phi and T which satisfy this property, and now I will make a statement. And the statement is as follows. If this is the case, then phi is equivalent. So let me maybe write this for equivalence to some theory T prime, where T prime is a subset of this T, which can be also infinite, T prime. Okay, so
equivalent means conjunction. When you say formula is equivalent to theory, it's equivalent to the conjunction of all the...
Yes, so if I have every model of a formula is a structure which satisfies every single sentence in the theory. and vice versa. Exactly. Conjunction, it would be infinite conjunction then, in the interesting case. This is why, yeah, it might be better to talk about theories. And so let me prove it maybe, because this is the crucial step. Okay, so I can even construct this T prime. I can tell you what is this T prime.
But sorry, but in the other direction, if phi is equivalent to some subset of the theory, then this also holds like this condition about A and B. Probably. So you say A satisfies formula phi, then A also, well, sorry, yeah, then A also satisfies T prime, then this B set of formals that are true in A also include this T prime, then B satisfies T prime, then it satisfies phi. Okay, yeah. So.
Okay, so maybe what you are saying is actually that one of these implications in equivalence is trivial. But okay, let's get to this. So sorry for moving, but when I touch the
Okay.
it moves a bit.
Don't worry.
So so I can construct this. I can define this T prime. So T prime is for me a set consisting of all formulae in T, which has this property that they are entailed by phi. Right? Meaning that every structure which satisfies phi also satisfies psi. And now I claim that this lemma holds for this exactly T prime. So one of the directions, right? We are proving this equivalence. So left to right is quite clear. So the fact that phi entails T prime is trivial, because notice that T prime consists of psi such that every psi is entailed by phi, so T prime is entailed by phi. Right? So there's nothing to prove. So maybe, Sasha, you were mentioning also this implicitly when you were, but okay, that doesn't matter. So the other direction is more interesting, okay? So let's prove the other direction. So I assume that my structure B satisfies this theory T prime. And now notice that to show that it satisfies formula phi, which is our goal, it suffices by the property stated in lemma to show existence of a structure A such that it satisfies these two conditions, right? So first of all, it needs to satisfy formula phi, and second of all, it needs to be the case that B entails exactly all the psi in T which are entailed by A. Because notice that this is what our statement says. And if this is the case, then B satisfies phi. So the goal is to construct this A. Are we fine? So for this, let me consider a theory. Let me call it S. And this theory will consist, first of all, of my formula phi, but then I will take also a set, infinite probably, of formulae not psi, such that psi belongs to the theory T and B entails not psi. This is somehow similar to my theory from the statement, but I'm looking at negations. Okay, so the goal is that I will be looking at A being the model, A model of this theory, and this will allow me to prove the theorem. But before doing this, let me first check if this actually is consistent, if this has a model. Okay, so let me suppose towards a contradiction that S is inconsistent. If S is inconsistent, then I use compactness theorem to show that I have finite subset which is already inconsistent. So by compactness, I have this finite set consisting of a formula phi and then some negation of psi1 to psi k, let's say maybe psi n, for finite n, which is already inconsistent. This is inconsistent for some psi1 to psi n from this set. Okay, so what does it mean is that we have that the formula phi entails this not psi1 up to not psi n. Is it fine so far?
No, wait.
No,
It entails
for me it's very strange because I
the
cannot even
without
imagine why
negations.
we consider this, but okay.
No, wait. It entails it without negations, or no? Because if phi is true, then sum of not phi has to be false, or in other words,
Yeah, you are completely right. That's the fix. Yes. Yeah, so now I'm just want to prove that this S is consistent. You will see why it's important for me because it will almost finish the proof. So if this is the case, then notice that because our T is closed under these junctions, and this is where we use this assumption, we obtain that this psi1 up to psi n is in our theory T, because it's closed under these junctions. Right, and moreover, we also can observe that it belongs to T prime, because T prime is a set of all of those all of those psis which hold in B. Okay, so let me move a little bit below, or maybe make it a bit smaller. Okay, so what we obtain is that this B needs to satisfy this disjunction. But on the other hand, we know that this B does not satisfy this disjunction because of that. So we obtain contradiction.
So say it again. Why B satisfies this disjunction?
So we have this disjunction being an element of T prime.
We assume that B satisfies T prime. I see now.
Yes, and we have an assumption in this direction which says that B satisfies the whole T prime theory. Okay, so I showed that it's not the case, so it means that S is consistent. And now the question is why I was doing this all. So that's probably 2 more lines. So now I can prove this lemma as follows. If S is consistent, it has a model. Okay, so let's take some of its models. And let's call it A.
So
So
A
by the definition,
satisfies phi, and B.
yeah, so this is what we obtained by the definition of S, because one of the elements of S is phi, exactly.
So B has to satisfy all formulas that are satisfied by A. And this is because all formulas because somehow it should follow from this construction of S.
Yes, so notice that by the construction of S, we've got the second part of S
Because
being
A doesn't satisfy all formulas that are not satisfied by B.
yes, so we can start from just rewriting by saying, just to make it clear, that it consists of this, so it satisfies all this formulae, right? And B satisfies not psi. So well, so now we can ask a question: what does it mean that some formula psi? Formula psi belongs to T and is satisfied by A. Well, then, if this is the case, then B does not satisfy negation of psi. What does it mean? Well, it means that B satisfies psi. Okay, so this means that B satisfies the set of all this psi in the theory which are satisfied in A. And this is exactly the second condition that we wanted to prove, right? So we have both of these conditions true, and we are done. So this is a technical lemma that is one way to prove the Losz-Tarski theorem. So is it fine? Are we fine with this lemma? Can we use it?
For me, it seems that really nothing is happening. So I just wait to see how you use it before I can understand what you use compactness, of course, but all other things are just more or less just.
Yes.
Okay, let's see how it's used.
Okay, so let's remember this lemma. So lemma says that whenever I have a formula phi and theory T which is closed under disjunctions, it will be actually used in the proof that it is closed under disjunctions. And moreover, that this if condition holds, then phi is equivalent to some subset of T. So I move down a bit and what I want to do, or what I can do, is before going down, I can move my lemma just to have it close to us. So the lemma, where is it? Lemma is here. Let's move the lemma. So we've got lemma. Let's put it on the side. And we are starting proving Losz-Tarski theorem. So let me recall that we have two directions to prove. So one is that if a formula is universal, then it's preserved under induced submodels, and then the other direction. So one direction is easy. So let's start with the easy one. So the easy one is to show that if a formula is universal, so let's say that assume phi is universal. So it is of the form, let's say, for all x1, for all xn, some formula psi of x1 to xn. And we want to prove that it is preserved under induced submodel. So it means that if we assume that some structure A satisfies this formula and B is an induced submodel of A. Okay, we said we want substructures. Substructure. Then we want to show that this formula also holds in B. Okay, and this is actually probably trivial, so I don't know if I should even write it, but well, if this is universal formula, then what I can do is I can fix some elements B1 up to Bn from my model B. And I won't need to show that this structure B satisfies formula psi, which recall is quantifier free with these elements. Okay, but since B is a induced substructure of A, that it means that every element which is in B also holds in A. And A satisfies this universal formula for all x1 to xn psi, which means that A also satisfies psi of this B1 to Bn. But if this is the case and B is induced submodel, then B also needs to satisfy this formula.
Yeah, I mean, that's more or less clear. It's just for every holds A, then for every holds in the restriction. Like that every partial order you can consider a restriction would be a partial order. Let's see.
So this direction is probably trivial, right?
Yes.
So the interesting one and the one that will use our lemma is the other one. So the other one says what follows. Let's say that assume that phi is now preserved under induced substructures. So I want to use this theorem, this lemma that we have with some theory. So, well, what theory we will use? Our theory T, corresponding to one from the lemma, B will be the set of all universal sentences. Right, so all P1 sentences, infinite set. So notice that clearly T is closed under this junction. So it satisfies the assumption that we have in the lemma, right? So I can sketch it somehow. So if I have for all x, phi of x.
Well, I mean, it's like closed, but in a sense of equivalent formulas, not that literally a disjunction to formulas. The universal formula is but there exists an equivalent universal formula. But that's fine, I guess.
Okay. So in this sense, exactly. Yeah. So we can find equivalent formula. Okay, so it satisfies what we wanted, and we want to show that there is T prime, which is a subset of T such that our formula is equivalent to this T prime. Okay, so notice that we are talking about really saying we want to claim that formula phi is equivalent not to a theory but to a single sentence which is universal, but actually by compactness theorem it suffices to show that phi is equivalent to some potentially infinite theory which is universal. Is it clear, or we need an argument for that?
No, I guess if it's not, wait, so okay, let's see. So if it's equivalent to T prime, whenever phi holds, any formula in T prime holds. And then you want to say, assume that no, so I just want to consider a theory phi and negations of.
That's quite simple. Notice. So if assume that we have this equivalence, right? So I will claim why this is enough to talk about theories. So assume that this is the case that phi is equivalent to some infinite theory of universal sentences. If this is the case, then in particular we have that phi, let's say, entails this T prime. The other direction, right? Where is the... So we have that T prime entails phi. So by compactness, there is finite. Bis such that this T bis entails formula phi, right? So you have a finite theory which is equivalent to formula phi. Okay, so I'm just claiming that it's really enough to show that we have T prime which satisfies this equivalence. And this is what I want to prove, because this is what we have in the lemma. Do we need any more discussion about it, or it's fine that
it's clear.
Okay, so this is what I want to show, right? And this is where the main part of the proof is actually. So I want to show that there exists a finite, potentially infinite theory T prime, which is a subset of T. So it's a set of only universal sentences, which is equivalent to my formula phi. Okay, so by lemma that we have, for this, it suffices to show the statement that we have here. This one. So it suffices to show that if I have some structure A which satisfies formula phi and B satisfies all these psi's in theory T which hold in A, then B satisfies phi. Because if this happens, then as we have in the lemma, phi is equivalent to some subset of T. Okay, so now we'll use again compactness for this. So we assume that this part holds. Okay, let's call it star. So we need to show that B satisfies formula phi. So I again consider a theory.
So once again, let's try to understand what's. So we have a model where the formula phi holds, and we have a model that has only that has where all universal formulas that are true in A hold. Okay.
Yeah. I have two models, A and B, two structures, and A satisfies formula phi, and B satisfies all the formulae of my theory, which means that it satisfies all the universal sentences, which are satisfied by A. So it agrees on.
So and what's the plan? So we want to somehow use here the preservation of phi. So if B would be just the substructure of A, we would say, okay, B satisfies phi just because A satisfies phi. And you want to use something to say that basically you can assume that B is a substructure of A?
Induced, yes.
Okay.
Yes. So for this, what I want to do is I want to actually, use this fact, let's say, or this idea of being a substructure by saying that I take a theory now, which contains formula phi and what is called a diagram. So I don't know if, okay, I'll write it down. So it consists of diagram of B. So diagram of B will be a set of all formulae, atomic formulae. So this is atomic. Right, so no Boolean connectives, no quantifiers, nothing like that, such that it is satisfied in B. And I do exactly the same with negations. So I take all atoms and all negations of atoms. Which hold in B. So somehow this is the description
What
of.
does it mean that an atomic formula is satisfied? It's not a sentence. Or what do you mean?
I guess one should add constants.
Yes, so you can use constants, for example, yes. So there are no free variables. There are no free variables. It is usually called this thing.
Okay, so you can, so basically, okay, you add enough constants. Well, I don't understand. So what, so if there are no constants, so you need to add constants. Sorry. And how many constants, the size of B or something? And how the models are extended to these constants defined?
So I'm not sure if you need really to add these constants really here.
No, but I mean, maybe you just.
I guess that at some point you should consider the diagram, because this is just the most, just the core of the proof. But I just am waiting where you consider this. I thought it would be here.
Said this word, but maybe I don't understand what is a diagram. What?
No, okay, no, but I can explain how one can reason. But maybe we should finish if we are close to the end, and then I can try to reformulate this in terms of diagrams.
Okay, so I wanted to call what I marked here as a diagram, but if you have a
Do whatever you want. Just no problem.
okay, so we are very close to the end. So maybe let me give the argument, and we can think about this introduction of constants if they are needed and how. So I want to show that S is consistent, and from of S being consistent, I want to show existence of a model. So that there will be a model, and then I will show that this model is such that B is an induced submodel of, and this will finish the proof. So just two steps really. So first of all is that we need to show that S is consistent, so it has a model, and this is again by contradiction. So suppose S is inconsistent.
But isn't B the model? No, we don't know. We don't know B.
Formula phi. So if you don't have phi, then yes, B is a model of this. But if you have a formula phi, you don't know if B is a model of.
Once again, because otherwise I will not understand. So atomic means that you take some constants that are indexed by elements of B, and you just add them new constant that weren't in the initial theory, initial signature, and you just take atomic formulas, you put these constants into these formulas, and whenever those that are true in B or false in B, you take with negations.
Yes, I think you need to add these constants, yes.
Okay.
But T is the set of all universal sentences. They includes all possible constants. We have no problem with the constants. There are a lot of them.
We might have no constants initially in the signature, I guess.
In T, we have all universal sentences. They include all universal sentences, including all possible constants.
Well, I don't know what is the. What I'm saying, what is the signature? Initial signature doesn't include no constants.
No, I believe that at some moment we should add constants for all moments of some model, because this is what is done.
Well, I imagine that we add all constants
okay.
for all elements of B. Then it would make sense.
Yes, and I think this is
idea.
the place that we need to do this. Yeah, because we can think about a signature which is relational. You don't have any constants, and then you really need to add them. Actually, in this point, I think
you need not just one constant. You need a constant for every element of the model. Otherwise, you don't have a bigger model somehow. But okay, let's. I'll try to comment later. I don't want to interrupt you just now.
Okay, so just quickly. So if you have if you suppose that S is inconsistent towards contradiction, I want to obtain a contradiction, right? So if this is inconsistent, that it means by compactness that there is finite subset of S which is already inconsistent. So it means that there is a finite subset of this diagram of B, which together with phi is inconsistent. So we can say, yes, by compactness, there is finite, let's call it D, subset of this diagram of B, such that my formula phi entails negation of this D. Okay? And now, what is this D? Actually, we can say that this is some atomic, or maybe not atomic, but Boolean formula without any quantifiers. So it has some constants. maybe psi would be a better name for that. Okay, so this formula entails that. So in particular, what we have is that formula phi entails also for all x1 up to xn, I have not psi x1, xn, because these constants are elements which do not occur in my formula phi. And phi is a formula which holds in my structure A. So by this entailment, I have that in structure A also holds this universal formula. And since this is universal sentence, then B, we obtain also needs to satisfy it. But we know that B satisfies this formula psi of B1 to Bn, so this is not true, because this
Yeah,
psi
but
is a part of the diagram.
what is the why A satisfies this formula? I lost track.
So notice that we assumed that A satisfies formula phi, and phi entails this universal formula. So it means that structure A needs to satisfy the universal formula.
Uh-huh. Then B should but it's from okay. So we assume that B satisfies all universal formulas that's satisfied in A. Okay, yeah. All
And
right.
this is universal sentence that I have here. So if A satisfies it, then B also needs to satisfy it.
Yes.
So now I think we are left with just one really line. So S is, let me put it here. So S is consistent, right? So S has a model. So that it means, so S has a model.
Okay. So and B can be considered as a substructure of, of this model.
Because, yes, so because M satisfies this diagram of B, we obtain that B, as you said, is an induced substructure of M.
Constants have to be distinct. I mean, why constants has to be interpreted? Why this is injective for constants in because we assume equality, so we have all the inequalities if we want.
I mean, I don't think you even need to assume equality in the language.
No, I mean, I guess you want to finish the proof, say, okay, so S has a model. In this model, there are all interpretations of all the constants that correspond to elements of P. And then
Yes.
Essentially, this gives us a substructure which is isomorphic to B. But the problem is that the constants can be interpreted. I mean, in principle, in this model of S, two constants that correspond to distinct elements, or maybe because it is like a homomorphism in the sense that it preserves the value of. So it's not an isomorphic. So this substructure of the model of S is not like isomorphic to B, but it's how it's called, elementary equivalent to it, because we don't really need, right?
I mean, it satisfies the same diagram. So in this sense, it satisfies exactly the same atomic and engagement sort of atomic formulae. So in this sense, it's equivalent on all of these formulae.
Yeah. Okay. Probably yes.
And because it's induced substructure of N, and we have that it's phi is preserved under reduced submodels, then B entails satisfies phi is immediate, right? So this is the end of the proof.
So yeah. Okay. Well, I think we
maybe we have to finish soon. Maybe I can just explain how I understand the proof, why it's true, and how one can come to this strange thing. So just to kind of position this in model theory. So imagine we have some structure A, and we have some theory T. And let's ask a question, is there a bigger structure B where T is true? So we have some structure which is not a model of T, maybe, but we want to construct a bigger structure that is a model of T. And then somehow there is a diagram argument which was, I guess, used. And the diagram argument is like this. Let's make a constant for every element of A. For every element of A, we have a constant. And let's add everything we know about this constant. That some predicate is true for, if it's true for A and B, we write this. Or we write no, it's false. Or we write that the constants are different. So we just try all the information without quantifiers that we know about the constant. And add all this add to T. And now the observation is that our goal is equivalent to consistency of this theory.
our goal, which goal?
Our goal is to construct a bigger model B where T is true. So we have a model A and theory T.
Is it possible to comment how is it connected to the initial theorem? Maybe it would be easier to follow.
No. It's better in this direction. I just want to explain the main argument, the main core argument, and then just wait a bit. So that if we want to extend a structure to a model of a theory, we just add to the theory.
But A is not a theory. A doesn't.
A is a model. As structure, sorry.
What do you mean then extend? Like why would we want to
construct to add new elements? To construct we construct A needs to be a substructure of B.
No, we take B equal to A.
But we want B to be a model of T.
Yes. So A is a model of T, take B equals to T. I don't understand.
No, A is not a model of T.
A is not.
A is just arbitrary structure, and we want to extend it to a model of T.
Okay.
So, for example, I don't know, we have natural numbers, and we want to extend it to a model of group theory. Then we add negative numbers or something like this. Just we have a structure and we want to construct a bigger structure which is a model of T. This is our model theoretic goal. And it has a very clear formula meaning, which is, let's consider what is called a diagram of A. It is just all the information about elementary predicates and functions which are in. So if f some function of a is equal to b, we add formula that f of ca is equal to cb. If it's not equal to b, we add that it's not equal to cb, and so on.
Yeah, okay. And these formulas should be consistent with T.
And this is an obvious remark. What we need is just this formula to be consistent with T, because if they are consistent, then we have we can find the value of the constants, and this will be a copy of A. So B will be, our model will be contain A inside. And if they are inconsistent, then of course such a B cannot exist. So this is just kind of obvious thing.
Yeah, and how you take a formula phi, which is preserved under substructures.
This is step number 1. Step number 2. Imagine that we have no structure and want to construct two structures A and B, and such that in A1 all T1 in A is we have two theories, and we want the smaller model be a smaller structure be a model of one theory, and bigger structure be a model of second theory. So before we construct, we have a fixed structure inside and want to get an extension. Now we have no structure, but have two things. We have our two theories, and we can take any smaller structure and any bigger structure.
Oh, but I don't understand. So far, I mean, I don't know where it's going. It's like it was promised that it would be some kind of easy, motivated reformulation of the proof. But so far, it's just some random formulas, structure.
No. Okay. No, if you don't like it, I cannot do anything. But just the idea, I want to explain the technical tool. Technical tool, if we want to extend the structure, we need to construct a diagram and add it to a theory which we want to be true.
Okay, that I understood.
This is main technical tool. And now I can formulate when it's possible to find two structures, that the smaller structure is model of T1 and the bigger structure is model of T2. And knowing the statement of the theorem, you can guess what is the condition. The condition
You
is
have two theories, and you want to construct.
You get two structures, which one theory is true in smaller one, and other is smaller, and other is true is a bigger one. And then I claim that we should have this thing. So this is possible if and only if T1 is consistent with all universal consequences of T2.
T1 consistent with all universal consequences of T2. So why it should be?
Because if no, in one direction it's obvious. If we have this A and B, then all consequences, universal consequences of T2 are true in B. Therefore, they are true in A, and T1 is also true in A. So we have a modal.
Yeah.
And in the other direction, we just use the previous thing. Imagine this is consistent, and let A be a modal. its modal. And then we want to show that then we use this one. We need to extend our A to the model of B. So because we already have tool of extending modals, now we constructed a model of T1 and want to extend it.
So
And it's also more or less straightforward. So imagine we need to show that a diagram of A plus T2 is consistent.
if it's
And
inconsistent,
imagine
you want to say that it's just consistent with all universal consequences. So wait.
no, yeah, we start with, we know that our theory T1 is consistent with all universal consequences. And then we construct a model for this union, and then extend this model to above. Since we have a tool of extending models but not contracting them, we should first construct the smaller model and then construct a bigger one. And the smaller model is constructed as a smaller structure is constructed as a model of this thing. And it will be automatically a model of T1, but then we should show that it can be extended to a model of T2.
Yeah.
Which means that this thing is consistent. Yeah? Now, if not, what does it mean that if it is not consistent? It means that in T2 we can prove that negation of some quantifier-free statement of some constants CA1, CAN. When okay, let's write this. When this quantifier-free statement is in the diagram, it's a conjunction of statements of a diagram to be.
Yeah.
Yeah, and so if we prove, but these things are new constant. So actually, in T2 we can prove that for every x1, xn, we have not this quantifier few formula of cx1, xn, because this formula with constants which are new in theory, it is exactly like variables, and so we can prove this thing.
Okay, and then it's not consistent.
And then this is just consequence of universal consequence of thing.
So, but it doesn't fall in A. Yeah.
Yeah. And final step is that if A is a formula phi and B is formula not phi, sorry. Then what is the claim? So we can construct a counterexample to extension property So our formula phi is not conserved with extension if only and if there is a
Sorry, in
zero.
P are structures, and now you say that they are
Oh,
sentences.
sorry. It's my fault. Of course. What I really want to say, sorry. Theory is phi, and T2 is not phi. So then this question about two structures A and B is just a counterexample of the fact that phi is stable under extension. And then
stable. Yeah.
So this task is possible only if phi is unstable. And we know when this is possible, when there is a universal consequence of not phi that contradicts phi. So this is some psi. So not phi implies psi, and psi implies it contradicts phi. So phi implies not psi. So they are just equivalent to negation of this universal statement.
What? But it's not what we want. We want to show that
Why?
phi. You are showing phi is unstable if it's equivalent to negation.
No, phi if phi is stable, if and only if the task is impossible, and a task is impossible if and only if phi is equivalent to a negation of a universal formula. That means it's equivalent to an existential formula. Phi is stable under extensions if and only if phi
You
is
are now
equivalent
proving the other version, I understood.
No, I can the same. I can write here not phi and here phi. They are completely symmetric.
Well, okay, so I could follow again, but it didn't look too much more natural than the other proof. Probably they're just the same.
No, I guess they're the same. But here is a kind of why I think this is more, because we do some clear steps. First, there is a clear tool of diagrams that we want to extend a structure to a model of something, and then we apply this argument about constant and variables to convert it into constructing a two model.
Well, maybe if you do this like in the other order from the third step, and then it would be maybe more.
Okay, no, but you can, of course, you can formulate things going in this direction, but look the
No, I mean just giving the feedback if you want. If you don't want feedback, I mean that's fine.
No. So you what do you think?
No, I mean it's like again the first two steps of the proof seem a bit ad hoc, random, and then something happens and probably it works out. I didn't quite follow it right in there.
No.
Maybe, but
no. But I think that the
I mean, what you're saying probably that you have to think it by yourself, and then it would be.
No. What I am saying that the first question, when a structure can be extended to a model of something, is not less natural than the theorem itself. So you may just it's a kind of model theory. We want not to construct any model of theory T, but a model which is extension of some given structure. It's a natural question, and it has a natural answer.
No, I mean it's just it's a natural question. Maybe it's first better discuss how it's connected to the initial question, because otherwise we say
why we should consider this as initial question.
No, I mean let's consider decide which question we consider. I mean
okay, but just the question to the speaker, is it actually the same proof or different proof?
I think it looks almost the same. Probably
It's probably the same.
rephrasing a bit, but the
Yeah. You know,
the same.
But is there some essential? You say that there are many arguments. Is there some essential different argument?
I'm not sure. But we also use diagrams, compactness.
No, but maybe there is some third argument which is clearly different from both. If you
I cannot see for now.
Okay. But this completely is I don't know how to do anything with homomorphism or whatever. So it's just for this original Tarski theorem.
I think what is also interesting is to see this example why this does not work in finite. So we see that this proof does not work in finite.
Maybe you can say this example if it's simple. Just say in 5 minutes something, and then we will see whether we understand it or not.
I can say it in 5 minutes. So
yeah.
Consider a signature, so maybe without writing to be quicker. So consider a signature in which I've got identity, I've got smaller or equal order, and some relation, binary relation R. So my formula will look as follows. At first, I define that this smaller or equal relation in my model is a linear order in the sense that it's reflexive, total, antisymmetric, and transitive. I can write a formula which says this. So smaller or equal works like standard smaller or equal over natural numbers. Then I have two more formulae. One more formula says that I can have R binary relation between two elements in my model. Let's think about them as natural numbers because we already have this similarity of smaller or equal to the natural number of natural numbers. So I can write a formula that R xy holds only if this is the case that y is the successor of x, understood as successor in natural numbers. And I've got one more formula. The last formula is probably a little bit more complicated, but what it implies together with the first two formulae as a conjunction of these three is that this third formula holds in the model only if this is the case that I have no cycles. And what I mean by cycle is that I have natural numbers such that first element is in relation R with the second in relation R with the third, with the fourth, with the sixth, and this last one is in relation R with the first one.
But how can you write as a formula if you don't have a length of cycle?
Yes, so I cannot write it as a formula, but I can write, but I already know that smaller or equal is a linear order by the first formula that I defined.
Then there is no cycle,
But I'm now talking about cycles with respect to R, successor relation, almost successor, something which is not more than successor. So there is this tricky formula which, together with the first two, uses this linear order of natural numbers, and on top of this builds another formula which implies what I said. I can write you a formula, but we will need some time in order to understand it. But this is what it implies, at least. This is what I can claim, and this is what one needs to prove. And this is a finite formula.
No, maybe you can just, at the end, you can write this on a board, and then we can then look on the board after your talk and think about this.
So let me just quickly write. So I can write a formula phi, which is...
So the language contains order. Just one binary relation.
And the second relation R.
And the second relation,
So this phi lin says that this is reflexive, total, antisymmetric, and transitive. So this is total
linear order,
For every there is a successor.
So not really. This one says that it's not more than successor. So it means that whenever I have, let me think. So whenever this is the case that x is smaller or equal to y to z. So of course this one we can define if we have then it cannot be the case that y is a successor of right? Okay, so if there's something between that x and y in terms of the linear order, then it cannot be the case that rxy. Okay, so rxy only.
But then the first is strict also, yeah?
No, it does not need to be strict, I think.
But then why don't you write that x is smaller than y? Because that will be equivalent.
You're right. It needs to be yes. Yes, you're right. Of course, it needs to be strictly between. Yes, of course. Yes. This is what I said.
Yeah.
And the third one, now I need to look to write it properly. So let me do this. So the third one is as follows, and maybe we can finish with me just writing this without saying much more, because if you want to say what does it mean, you really need to prove what I said, that it entails this secrecy. Okay, so that's the third formula, and I'm claiming that the third formula together with the first two implies this equivalence, that it holds if and only if R is acyclic, in the sense that there is no sequence of elements in relation R which go back to the first element. So there is no cycle through R.
Okay, we should look at this. But just then you need to prove somehow that this formula is not equivalent to some universal formula in finite modals. And how can you prove this? What is the tool somehow?
Well, the tool, this is quite a clear, straightforward direct proof, constructive. So you say, okay, assume that it is equivalent to universal formula with k variables. So I will construct you a k+1 size model, which consists of k+1 natural numbers with the standard ordering of smaller or equal, standard interpretation of smaller or equal. And then I can have also some interpretation of R, which is, I think, successor.
Yeah, okay. So you just what you should get a contradiction considering how many variables are in this formula, and
so
then you construct a counterexample.
The
size of the counterexample will depend on the number of variables. That's what you are saying, I guess.
Yes. So basically, you've got a family of models of increasing size for every size of the number of variables, and you can show that none of those is good. So yeah, so this works like that. And the idea is that it has this loop R, and whenever I delete one element of the model, then it does not have a loop anymore, and that's the proof. But yes, so it's a constructive.
Yeah, okay. What we need to think, yeah.
Yeah, so what do you think we can? What's the next?
We can thank the speaker, I guess.
Yeah, we can thank the speaker, and what we will be doing next time.
But next time we have Don Stahl, I guess, next week, no?
Yes.
I thought.
Yes.
Let me check. But it will be in a non-trivial time. It will be at Tuesday at 5 Moscow time and 4 French time, and he will explain something about constructive dimension of lines and points.
Yeah. And then, so at some point we can also return to this, I think, right? To see
Yeah.
some.
Yeah.
Okay. That next week on Tuesday we have.
On Tuesday. No. Theoretically, we can have it on Monday, the continuation, but some people believe that there should not be 2 talks in 1 week, so then we can.
Yeah. So maybe in 2 weeks, I don't know. I don't know, Przemysław, when do you available more or less?
Let's maybe do this offline so I can check my calendar properly and
Okay.
Yeah.
properly, and then we can set it.